Hello and welcome to this session on circles. Before we look at circles, we're going to start looking at really basic facts and gradually build up. So the first thing to think about is the angle on a straight line. So obviously the angle on a straight line is 180 degrees. The angle at a point, so all the way around, is 360 degrees. So really basic facts, really important. And then, of course, angles in shapes. Well, the angle in any triangle is 180 degrees. And the angle in a four-sided shape, well, remember, a four-sided shape, quadrilateral, could be cut into two triangles, so that's 360 degrees. So it's really important to remember your basic angle, your angle facts when you're going to be working with circles. A few more basic ideas before we go on to any circles. So if you've got two straight lines and they cross over each other, then the opposite angles are called vertically opposite, and they are the same as each other. So the other angles here, this one and this one, are also the same as each other. So angles in an X vertically opposite and equal to each other. And another important fact is that when you've got parallel lines, these angles here and here are the same as each other. If you see what's going on here, it's a bit like a backwards Z. So they can sometimes be called Z angles. And this angle will be the same as this angle. And the final example before we go on to circles are corresponding angles. So these can be called F angles. And that's because we've got something rather like an F in here. So these angles are the same as each other as well. So that's just a reminder that you do need to remember your basic angle facts before you start thinking about circle theorems. So now let's have a look at a circle. Okay, so I've shown the centre of the circle as C and the radius as R, and then drawn a tangent to the circle. So whenever you draw a tangent to a circle, it just touches the circle, and you can see it meets the radius at that point at right angles. So that's really important, that when you've got this situation, the angle between the radius and the tangent is 90 degrees. So that can be really important. So that when you draw two tangents from a point, like this one here, so we've got one line meeting a circle over there, another line meeting it in a different point, then we actually get two triangles that are exactly the same shape as each other. So what I mean by that is that they've got this side in common. They both have a radius of the circle. They share this side. So the other side must be the same. So in other words, these two triangles have exactly the same sizes in terms of angles and lengths. So those are both right angle triangles. So that can be important when looking at circles. Next thing to look at is when we have got this sort of situation. So both of those triangles there involving two radii from the center of the circle and one other line. So the important thing there is that whichever of those triangles you've got, these two angles are the same as each other. So it's because these two sides are both the same as each other. So both of them represent the radius of the circle. And although this looks different, it's exactly the same sort of thing. We've got a wider angle in here, but we've still got a radius there and a radius there. So those two angles are the same as each other. So in both cases, we've got an isosceles triangle. Okay, so let's now have a look at another example. So here we have got a circle being cut by a straight line, and that's called a chord. Now, if we cut that line in half, with a perpendicular bisector, then that line will pass through the centre of the circle. So that's what we've got over here. So I've got a chord of a circle. I've drawn a line which meets the chord at right angles, and it cuts it in half exactly. And then if that happens, that line must pass through the centre of the circle. So those are some really basic ideas. The next ones are a bit more complicated. So let's have a look at what comes next. So this one, very important. So the important fact here is that if we've got 2 points on the circle and we draw across to the other side of the circle, we have this angle A, then the angle in here is twice angle A. So this is 2A if this is A. And we can show why this happens, and it comes back to the idea of the isosceles triangles that we looked at earlier. So the explanation is over here. So what I've done here is I have drawn in an extra line so that we've got a radius of a circle there as well as here and here. So you can see here that if these two angles are both x, we know they're the same because the two sides here are the same. And these two angles are the same as each other. So if they're both y, then the angle over here is x plus y. So the angle here is 2x plus 2y. In other words, the angle at the outside is half the angle that we get there. So that's a really, really important fact that often comes up when we're looking at circle theorems. And a special case of that is when this angle over here is a right angle. So this is a right angle, then the angle at the centre is twice that, which is 180 degrees, so it's a straight line. So that's why we say that the angle in a semicircle is a right angle, it's 90 degrees. And then following on from that, it doesn't actually matter which point we choose here. Wherever we choose a point, this angle here is always going to be double this angle. So this angle must be the same as this angle. I could have chosen another point up there, and then that angle would be the same as those two angles. So there's lots of possibilities in terms of choosing points here. So long as they're all above this, this chord here, then these angles will all be the same as each other. And then looking at the reverse situation, so let's remind ourselves what we just looked at here. Here we just looked at the angle A and the angle there being double. What we're going to look at next is the opposite angle, this angle here, and then draw in a point down here. So that's what we've got here. So this now looks slightly different, but it's exactly the same idea. We have got the angle at the centre being twice the angle at the outside on the circumference. And because that happens, then the two angles A and B must add up to 180 because the angle at the centre is 360. So that's what we've got happening down in this example here. This angle plus this angle add up to 180. And the way to say that is that the opposite angles of a cyclic quadrilateral add up to 180 degrees. So a cyclic quadrilateral is one which has its four corners on the circumference of a circle. And you can see that if these two are 180, we know that all the angles in a quadrilateral add up to 360. So these two must also add up to 180. So opposite angles add up to 180, whether they're here or here. So the next one we're going to look at is the alternate segment theorem. So let's just remind ourselves of what a segment is. So a segment is, if we've got a chord in a circle, this is a segment one side of the chord, this is a segment the other side of the chord. And the actual theorem basically says that the angle between a tangent, so that's a line just touching the circle, It's the angle between a tangent and the chord. So this is the chord here, and that's equal to the angle over here, which is standing on the chord in the alternate segment. So this is one segment, and this other bit down here is another segment. And if you want to see why that's true, what you can do is, as I did earlier, draw in some more lines on the diagram. So what we're going to do is draw in a line to the center from there and another line there. So that's what we've got in this diagram at the bottom left-hand corner. And if we do that, again, we can see that we've got an isosceles triangle down here. So if we say this angle in here is x, then this angle must also be x, because it's an isosceles triangle, because that's the radius, and so is that the radius. So this angle, because it's a triangle, must be 180 minus 2x. And this angle over here must be half of that. So that's 90 minus x. But here, this is a right angle, so this must be 90 minus x. In other words, this is the same as that one over there, which is what we've got here. So this angle here, the same as that one over there. Right, so that's a quick whiz through the basic theorems. So now let's have a look at some questions. And put those down there and cover up one of the ones we're not looking at, so we can concentrate on the actual question. Right, so what is angle x? Any ideas what x is going to be? So here we've got triangles. We're thinking about triangles and the circle theorems. How are we going to find angle x? Well, one possibility would be to think about this angle here. What does that tell us? If we've got 72 there, and this is a straight line, we could write down either this angle or that angle. And we know those two are the same as each other. And it's probably more useful to write down this one here, because if we're trying to find x, we would be able to find it if we knew the other two angles in that triangle. So what we're going to do is just say, well, this angle here must be 180 minus 72. So that's going to be 108. So that's looking good. But we also want to find this angle over here. Once we know this angle, then we'll be able to write down what x is, or work out what x is, because x is going to add to these two angles to make 180, isn't it? So this is where we think, this angle here is going to be the same as this angle here, because both of these lie on this arc over here. If we look at those 2 points, then this side, this angle, 41, must be the same as this angle over here. And then the problem simply becomes, what is the third angle in a triangle? And what is the third angle in that triangle? We know we've got 108 and 41. So we know that the angles in a triangle add up to 180. So x is going to be 180 minus 108 minus 41. So x works out to be, well, that will be 72 minus 41. So that's going to be 31 degrees for angle x. So that, another way of doing it would have been to find this angle over here, because this angle is the same as that angle there. So that actually is also x. Right, so that's that one done. Which one should we look at next? Shall we do that one up there? So let's just cover up this one so I'm not looking at too many things at the same time. So angle A. So here we've got a point that's not actually on the circle. So it's no good sort of thinking about anything that's involved with things inside a circle. This is a point outside the circle, but this should look familiar. Think about what we looked at earlier on. We had lines like this just touching the circle, and they were called tangents, weren't they? And do you remember we said that this would be symmetrical? So we can see that this length here is equal to this length here. Therefore, these two angles are going to be the same. So this angle over here is 59 degrees. So again, we're coming back to a triangle, and as someone's just put in the chat, angles in a triangle add up to 180. So that's all we need to do. So although sometimes people think circle theorems are very complicated, very often they come down to what do the angles in a triangle add up to. So yeah, the first question we looked at involved angles in a triangle, and so does this one. So we're using information about a circle, but also we're looking at the idea of this being an isosceles triangle. So the angle A is going to be 180 minus 2 times 59. So what's that going to be? So 180 minus 118, and so that's going to be 62 degrees. So again, angle in a triangle. So next one, the first one. So if you can see that one. Right, so it looks a bit unusual. We've got another tangent, but this time we only got one tangent line, no, not two tangents. We've got a radius. We've got an angle of 20, and we're trying to find this angle y here. So again, we've got this idea of triangles appearing. Yeah, there's a triangle here. We're trying to find y. How can we find y? So it's a circle problem to begin with, but then ends up being a triangle problem. Now, the important thing about this triangle, we said at the very beginning, if we've got a radius and tangent, which we've got there, then we're going to have a right angle. So that's good. We've got y, 90 degrees, and an unknown angle. So we need to find this angle in here. So now we can forget about y and just look at the circle and think about how can we find this angle? So this is the angle at the center. We know the angle at the outside. So this is one of the theorems we looked at earlier on. And we know the angle at the center is double the angle at the outside. So this angle in here must be 40 degrees. So that's the hard bit done. So we now know that y, coming back to angles in a triangle again, y is 180 minus 40 minus 90. So y is simply going to be 50 degrees. Actually, remember with these questions, they tend to be not drawn to scales. That's deliberate so that you can't just measure the angles to work them out. Obviously, if you look at what I've got drawn here, this angle here looks bigger than that angle here, but these are drawn like that to mislead you, to not help you. Right, so one more question. And that must be this one down here. So this one is, again, got loads of triangles in it. So although it's a circle theorem question, it's very much looking at triangles. I can see loads of triangles there. So this is a bit unusual, isn't it? Because normally the unknown just appears in one place in these kind of triangles, because in these kind of questions, rather. I'm seeing so many triangles. Right, got triangles on the brain. Right, so how are we going to find D? So what we have got to do is find D. We've got a D there and 2D there. And we want to know what is D. How can we work out what D is? So what the only thing we're given, well, I suppose we're given two things. We've got 28 degrees given there, and those two lines there are telling us that this is an isosceles triangle. So we know that these two angles down here inside this isosceles triangle are the same as each other. So let's have a look at how we can deal with that then. So we've got this angle over here, which is standing on this arc here. but so is this angle over here, which is good, because otherwise we didn't know anything about that triangle. So now we have that that's 28 degrees. And given that we've been told that this is an isosceles triangle, it's very likely that will help us if we can work out these two angles down here. And in fact, it will help us, won't it? Because then we'll have a straight line where we know that we've got D, 2D, and this angle adding up to 180. So that will sort it. So what we need to do is look at this triangle here. So we're going to work out 180 minus 28. So that's going to be 152. We're going to divide that by 2. So that's going to be 76. So now we've found these two angles down here are both 76. And obviously the important one is this one, because then we have got, move this up a bit so you can see what I'm doing. We then have the angles on a straight line. So D plus 2D plus 76. It's all on a straight line. So that adds up to 180. So D and 2D is 3D. And then we can subtract the 76 from 180. So that's going to be 104. I'm just checking, is that right? So we've got 76 and 76, 6 and 6, 140, 152. Yeah, 128, that's right, isn't it? So then 3D plus 76 is 180. So 3D is 180 minus 76, so it's 104. So what's D going to be equal to? That will be 30 something, won't it? Is it going to go in exactly? It's not going to go in exactly, is it? That makes it a bit hard. So it's going to end up with a fraction. So that goes into 102 exactly, doesn't it? So that's going to be 34 2/3. And that should be D right there, shouldn't it? Right, so does anybody have any questions? So we can write them in our blank circles. If there are no questions, then we'll leave it there and you can put questions later on in the comments. Okay, that's it for today then. Thank you and goodbye.